What's up, guys? Welcome back to another Algebra 2 instruction lesson here with Mr. Gaines as we continue to look at the FO.1 notes, which is arithmetic in composition of functions. Today we are going to continue our focus on function composition. The last time we met virtually, we had a discussion about the composition of functions and how it relates to substitution. How function composition is essentially taking one function and substituting it into another, replacing variables. Now we can also go through the process of decomposing a function, or essentially giving it an expression, determine what that expression or what the functions could have been to create this composition. So if we take a look at problem number 9, it says for each composition given, determine f of x and g of x and p of x when applicable. So in A, we have f of g of x equals the quantity 7x plus 3 squared plus 1. So in this instance, really, there's a different variety or a few different answers that we could possibly have. So essentially what I do with these functions is I determine what my substitution function is, what function it is that I'm putting into the other. And I usually denote those with parentheses. Now in problem number 9, there's already a set of parentheses, so I'm just going to use that for the example. So if I had parentheses around 7x plus 3, that means my function that is being substituted in would be 7x plus 3. Based on the notation that we see here, g of x is being substituted into the function, so g of x must be 7x plus 3. Now what that allows me to do is to determine what f of x would be prior to the substitution. So remember that in function composition or substitution, if g of x is being substituted into f of x, I'm composing those functions, 7x plus 3 is replacing an x value. So that means f of x originally would have been x squared plus 1. And so this is one example, one option of what this function composition could have been. G of x substituted into f of x given these two functions would result in f of g of x that we see there. Now a different way that I could do this is if I place my parentheses in kind of an abstract location, but something a little bit differently. So in red, I'll give you a different example. In this case, I'm going to claim that g of x was 7x. Then if that were the case, that means f of x would have had to have been x plus 3 quantity squared plus 1. In this case, I would be substituting 7x in for x in that location, which would still result in the function composition that was given to us. So there are different options that you could have here depending on where you determine the original substitution took place at. So generally, if the parentheses are there, we're going to assume that function is, well, within those parentheses, 7x plus 3. If not, we can place those parentheses where we choose. So let's go ahead and take a look at B. B is f of g of x. Again, g of x is being substituted into f. So let's say maybe I claim that g of x would have been the function within those parentheses, x cubed plus 5. That means that f of x would have been the result of that function composition would have been the square root of just x. So if I take x cubed plus 5 and place it in there, substitute in for x, then I have the function composition that was listed above. So this is one option. Now, again, we could do different options depending on where we determine the original function or the original substitution occurred. So let's say maybe I switch this problem up and I put some parentheses around x cubed. So here I'm going to claim that g of x was actually just x cubed. That means f of x would have had to have been the square root of x plus 5. So there's many different options that we could come up here. These are just two examples, but many different options that we could come up with here as we decompose functions and we determine what g of x or f of x would have been. Now we do have to be careful with the notation. Now if I said, these are both correct answers, but if I said g of x was actually x cubed plus 5 and f of x was actually x cubed, or sorry, g of x was the square root of x plus 5. and f of x was x cubed, that would be incorrect because we do have to make sure that the substitution order matches up with what we see here for the function. So g has to go into f. So if you get this idea, go ahead and pause the video and see if you can complete 9c and 9d. Hopefully you had a chance to do 9c and 9d. And I'm going to go ahead and give you, again, two different options that we could have here. So let's say that I choose that the function, the substitution occurred here, where the parentheses are marked. That means g of x, which is being substituted into f of x based on our notation, would have to be x squared plus 3x plus 4. And therefore, f of x would have had to have been 8 over x. So that's probably the route that most of you went. Now, let's say that I did this a little bit differently. Let's say that instead I assumed the substitution occurred at x squared plus 3x. That means that in this case, g of x would have actually been x squared plus 3x, and f of x would have been 8 over x plus 4. So again, both of these would be two different options that I could take g of x and compose it with f of x, substituted in for the variable, and then come up with the result that was shown above. Now in D, we have three options here, or three functions that we need to look at. In this case, what we have here is this statement says that p of x is being substituted into g of x, which is then being substituted into f of x. So this is three functions coming together in function composition. We would read this as f of g of p of x. So let me identify with a couple set of parentheses. Let me put my first set of parentheses right here. That means p of x would have had to have been the function 5x plus 7. Well, then if p of x is the function 5x plus 7, that function would have been substituted into this square root. So that would make g of x the square root of x. Now, if I take p of x and substitute it into g of x, this would be g of p of x, and you don't necessarily have to write this down, but that result would be 5x plus 7. So the square root of 5x plus 7. So the square root of 5x plus 7 we see in this location, which means f of x would be what remains outside of the parentheses, the cubed root of x. And so this would be an option, not the only option, but this would be one option that would represent the function composition here. So if I take p of x and substitute that into g of x, and then that result is substituted into f of x, I have the function composition shown. So this is function decomposition, many options, different options here, but basically it's just trying to get us to think about what could have been substituted to create the expressions that we see. Now our next topic deals with the applications of function composition. So essentially your word problems. So let's go ahead and just jump right into some examples. In problem number 10, it says the fixed cost to publish Relatively Made Simple by Way is $2,500, and the variable cost is $4.50 per book. Marketing studies indicate the best-selling price for the book is $9.50 per copy. In A, it says find the cost, revenue, and profit functions for this book. So first, in A, we need to find cost, and let's let cost be C of X. So cost deals with two different things. We have a fixed cost, which is $2,500, and a variable cost, which is $4.50 per book. The fixed cost means that that number value is never going to change. And so we can represent that cost with $2,500. The variable cost means that number could fluctuate depending on, in this case, how many books are being made. So what we don't know is how many books are being made. So let's let X be the number of books. And we're going to assume that the number of books that are made and sold are the same. So $2,500 is the fixed cost plus $4.50 per book. So 4.5 times X. This function represents cost. Now let's let R represent revenue. In this case, we know what the revenue is. Revenue would be the income created by selling the books. So the revenue generated is going to be $9.50 per copy. So 9.50x. Profit then. In this case, profit is going to be the cost, or sorry, the revenue, the amount of money that we bring in, minus the cost, the amount of money that we have to pay to create the books. So if I took 9.5x minus 4.5x minus 2,500, this would be 5x minus 2,500. So our cost equation is 2,500 plus 4.5x. Our revenue equation is 9.5x. If we subtract the two, we get the profit, which would be 5x minus 2,500. Now in B, it says determine how many copies must be sold for the company to break even. So essentially what we have here is the arithmetic of two functions. We subtracted the two of them. Now, to find out how much the company must sell for the company to break even would be assuming profit is going to be 0. So we can let 0 equal our profit. And this is a quick algebraic solution. You could solve it graphically if you want, but it's rather fast algebraically. And we'd find that 500 equals X. So how many copies must be sold for the company to break even? 500. So here we see basically some function arithmetic as we subtract the cost function, or sorry, subtract the cost function from revenue to create a profit equation. And then we can solve as we have done throughout the year. So this is something we have done before, but maybe not identified it in this way. Now, problem 11 is probably something that most of you guys can do, but we are going to identify it in maybe a potentially different way. So in problem number 11, it says, while traveling the Far East, Timi must convert US dollars to baht using the function b of x equals 41.6x, where x represents the number of dollars and b of x is the equivalent number of baht. Later, she needs to convert baht to Malaysian ringgit using the function r of b equals 10.9b. So in part A, it says to convert $100 to baht. So we know that we have 100 US dollars and we're converting it to baht, so we can use the b of x equation. So essentially what we want to find here is b of 100. So b of 100 would be 41.6 times 100, which would be 4,160. And you could find that, again, if we wanted to go to the calculator, we could find that. We could do 41.6 times 100, which would be, sorry, I put divided by 100. Let's fix that. 41.6 times 100, which would be 4160. Again, $4,160. Or sorry, not dollars. We're changing our units. 4,160 baht. Now in B, we then want to convert the result from part A to ringgit. So we can use this conversion chart here where we convert baht to ringgit. So we want R of B, or R of 4,160 baht, which would be 10.9 times 4,160. So probably want to do that in the calculator. And the result would be 45,000 344. So what we get here is $100 equals 4160 baht, which equals 45,344 ringgit. Now, let's say in C, we want to create a function that would go straight from dollars to ringgit. So what we can do here is we can do a function composition. So if we're going from one function into another, we can compose the two equations. So R of B gets us from ringgit to baht. B of X, gets us from baht to ringgit. B of X gets us from dollars to baht. So if we compose the two, if we take R of B of X, we can now go from dollars through baht to ringgit. So R of B of X would be taking B of X and substituting it into R of B. So this would be 10.9 and then replacing B with 41.6 X. So 10.9 times 41.6 would be 453.44 X. So here what we can do is we can find a quicker way to convert directly from dollars into ringgit. So if I wanted to convert from dollars into ringgit, like we do in part D, we're going to convert $100 again just to make sure that this works. But what we would be finding here is R of B of 100, which would be 453.44 times 100, which you could do in the calculator if you needed to, would be 4,344 ringgit. So we can see that this method here does the same conversion that we did previously, but in one step. So if Timi is now in Malaysia for a longer period of time and she spends all of her 45,344 ringgit from the baht that she had, and now she needs to convert more dollars to ringgit, she has a function that allows her to directly do that conversion here with part C. So you can see a little bit of the use of function composition here. Essentially substitution wrapped into one process. This is a good place for us to stop here. So when we reconvene in class, again, we will have the opportunity to go over questions and do some practice before you guys get the opportunity to test your knowledge over arithmetic and composition of functions. As always, thank you guys for tuning in, and I'll see you soon.